Today we are doing practice quiz 5, and practice quiz 5 is just a lot of reactions that we kind of just have to memorize. But I'll be going over like shorthands of the mechanisms so we can have a better understanding of what's happening. In our first reaction, we have a carboxylic acid and a acid chloride. And what happens is we're exchanging one of our oxygens for a chloride molecule. And this is going to be a reagent we'll have to remember, but it's pretty easy. It's SOCl2. In solution, this molecule looks like this. What will happen is chloride is going to spontaneously leave the molecule, which will move this. Try to move to the side so we have more space. Which will result in this OSCl. Negative. This molecule will then attack to this oxygen here and push down into, the pi bond will then push down to the oxygen here. And I think I'm missing some lone pairs here. Yeah. So then this results in R O H O S double points Cl. This molecule, let me check something. Yeah, that's right. Except it only has one lone pair. Okay, moving forward, the chloride that we just drew is going to add into the carbon we have here, which will push the pi bond onto the oxygen there. And this will result in this molecule, OH. S bonded to O. Cl. Then this step sort of happens all at once. This oxygen on top is going to take the electrons from the bond with the carbon and contribute it to the sulfur oxygen bond, that bond creation is going to have the sulfur push out the chloride, and to ensure that the central carbon here still has 4 things bonding to it, it's bonds from the ion pairs from the hydride are going to push up as well. Or it might be a little better to think of it as the hydride is going to attack the central carbon to reform the carbonyl bond, which then pushes out the OSOCl, right? But when that pushes that out, the sulfur is going to have too many things bonded to it, so it's also going to kick out the chloride. And then this ends up to this molecule after we get rid of this H. But we can get rid of this H because let me get a different color. We kicked out a chloride here, so we have this in solution, and it's just going to deprotonate that H and give the bonds there. So minus HCl minus SO2. We have gas, so this is a good even group. And then we end up with our final molecule here. Yeah, so that's how you do the first one. And for the second one, it's not too bad either. First, we have to recognize the ethyl 3 nitrogen. The nitrogen is a strong base, which means it's going to deprotonate stuff. And we see that we have an alcohol here that has a very convenient hydrogen that can be deprotonated. So when this molecule deprotonates that one, we end up with, this molecule is the beginning acid chloride here. And then we have this. It donates reactions there. And this is okay. The middle molecule is a strong nucleophile, okay, because it has lone pairs and a negative charge. So it really wants to not have that negative charge. So it's going to take a pair of electrons and attack that, which then pushes electrons up here. Electrons from the pi bond up to the oxygen, because carbon doesn't want to have more than 4 things bonded to it. And this results in this molecule. But now, this oxygen at the top has too many things bonded to it. So what it's going to do is push electrons down to reform the carbonyl bond, but then it's going to push out the chloride, which results in this. Your added-in molecule, your carbonyl that's happy again, and Cl in solution, your H and EC3. And if we think of this as a catalyst, we can we could think that maybe the chloride takes it back, pushes the own pair. So you have HCl plus and ET3 if it's a catalyst. Because catalysts are consumed and then regenerated in the reaction. But the only thing that you really have to draw is this molecule. And a really cheap shortcut is that this molecule is just the result of this part replacing the chloride. So that's a fast and furious tip if we want to just draw the molecule right away. Okay, for the next one, we have a dimethyl copper lithium. And how this works in solution is that we have Li plus Cu and your methyls, which I'm going to draw as CH3, CH3. Yeah, this has a negative charge. I don't know how many lone pairs it has, but the main thing you should know is that carbon is a lot more nucleophilic than the copper atom because of its placement on the periodic table. So I write them down. Carbon more nucleophilic than copper. So what that means is it's going to take the electrons in the bond between the copper because it actually sort of owns it because it's nucleophile, and it's going to use those electrons to attack our molecule here. This then results in the pi bond pushing up. So then this now has a negative charge. We have CH3 bonded here. But then, as we've seen in the previous example, the oxygen isn't happy. So it's going to push some electrons back into the carbon-oxygen bond. But then carbon isn't happy. So then it's going to push out the chloride. And then this results in this ketone plus C-. But we can have Cl minus in solution because if we look back to our original reagent, we have lithium floating around. And lithium has a positive charge that can neutralize the negative charge of the chloride. And then after, and then that is our final answer. We have a ketone now. And a fast trick for these methyl lithium. I know I'm not saying the names right, but I hope you know what I mean when I'm saying it. Is that these will always form ketones with acid chlorides. So always ketone with acid chloride, CH3. Next, oh, hold on. I'll specify that a ketone is this molecule with the R are just both carbon groups or alkyl groups. So we have a CH3 here, that's an R group, and the other R group is the benzene with the tail on it. But we know that this is a carbon, so it also satisfies being R group. So we've successfully made a ketone. Next, we have LPA and iodine bonded to ethene. For LDA, we should we can we I think we know how it works. It's just it's this nitrogen with two tails bonded to lithium. And this nitrogen has a negative charge and lithium has a positive charge. Lithium disopropylamide. Yeah. So we should recognize that LDA is a strong base because the nitrogen has a lone pair and a negative charge and it wants to be neutral and happy. So what strong bases do is deprotonate molecules. If we look at our starting molecule here, we have the ketone, and I'm going to explicitly draw out the hydrogens so that we have a better idea what's happening. I'll draw half of this molecule. And it just goes on. Goes on. Wait, we can draw squiggles. We can see that there's only hydrogens on one side, which is the white side. So then the nitrogen is going to deprotonate one for itself and push the bonds here. Oops. Push the bonds onto the carbon-carbon bond here, which then pushes these bonds up and forms an enolate. Something we should think about when we are working with LDA is that LDA is going to attack the esterically hindered side. So let's imagine, I'll draw it down here and erase it. I have this and then 1, 2, H, CH3, CH3. Which one is LDA going to attack? Is it going to attack the white or is it going to attack the left? It's going to attack the white side because these methyl groups here create a lot of sterics. And we see how bulky LDA is up here. It's gonna be it's gonna be really hard for LDA to attack the most sterically hindered side. So it's gonna go for the side that is the least sterically hindered. So next we are going to realize that oh, this alkene here is electron rich, so it can be used as a nucleophile to attack other things. In this case, it's going to attack this carbon here that's bonded to the iodine. And the reason it's going to attack this particular carbon and not this carbon at the far right side is that iodine is very electronegative, so it has a partial negative charge. And this carbon, as a result, has a partial positive charge between this bond here. The partial positive charge makes it kind of electrophilic, so then the nucleophilic alkene can attack that specific carbon. And because this carbon at the edge doesn't have like anything electronegative to it, it's pretty neutral. It's okay. So then when the alkene attacks that, we're going to recognize that the central carbon is not going to have 4 things bonded to it. So the enolate on top is going to push some electrons down and create a carbonyl group. Yeah. So we end up with this. 1, 2. You can draw the hydrogens here if you wanted. And one thing that we can do to make more sense of why the iodine molecule attaches to this alpha carbon and not the central carbon is because we could draw a resonance form for this molecule that looks like this. See? And all I've done to draw this molecule is push electrons down from the oxygen to reform the carbonyl, which then pushes the pi bond between the carbons to push onto the singular carbon, the alpha carbon, in fact, which allows it to have nucleophilic character, and then add in the ethyl iodine. And this here is the right answer for a pretty fast and tip to think about this is think that LDA is going to take out a hydrogen from the eusterically hindered side. So the ethyl iodine, or whichever molecule, is going to add into the steric hindered side, taking the place of the hydrogen that was lost. And that's how you solve that one. Next, it's kind of the same thing. So we should recognize that pyridine actually has a lone pair existing at the nitrogen, and that lone pair makes pyridine a base. And we should know that bases want to deprotonate stuff. And what can we deprotonate in this molecule? Well, I see there's an H here. And I think that's really the only H that's like acidic. Like, I could say that there's an H here, but that bit that hydrogen is kind of happy with where it is. It doesn't really want to be gone. And the H here, it's acidic because it's bonded to an oxygen. And oxygen is electronegative and kind of wants to steal, it's greedy, it wants to steal electrons. So what's going to happen is nitrogen is going to take that that hydrogen and then push the electrons between their bond onto the oxygen. And that's going to result in this. The first molecule is unchanged, but then we have our second molecule looking like this. 1, 2, 3. And then we realize, whoa, our oxygen has too many things bonded to it, and it has a negative charge. It's not really happy. So it's gonna attack something so that it can be happy again. And we can recognize that it's gonna attack using one of its own pairs. It's gonna attack this carbon here because, well, this carbonyl bond, the oxygen, is slightly negative, but this is slightly positive. And this then results in bonds, the pi bond, the electrons in the pi bond moving up to the oxygen because the oxygen can accommodate a negative charge, which then results in this molecule. You have a R bonded to a O bonded to this. This molecule looks really ugly, but we'll trust the process. But then, as we've made one oxygen happy, we've made the other oxygen unhappy. So what's going to happen next is the oxygen is going to push down a pair of electrons to reform the carbonyl. This is going to kick out the chloride. And then we get this other final molecule. Let me actually do a different color so we don't mess up what's happening. We don't confuse what's happening with the top color. So we end up with this. R, O, R, boom. Press CF. And You could, if we think we want to make Cl happy, we can pull our pyrimidine back into the mix. It has an H bonded to it. The Cl could very well deprotonate that, making HCl, and then regenerating pyridine catalyst because it gets the lone pairs again. Yeah. And a really fast way one can think about this reaction is the when an acid chloride reacts with a carboxylic acid, these are going to be retained. Or like these are what's going to be in the molecule. Whatever the C was here is just going to become the O, bonded to the O. And then you have the rest of the R group here. That's a really fast way to do this. So for our next reaction, we have the vineyard followed by H aqueous to the workup. And we can realize when we have an excess or yeah, we should know by now that Gwyneth's attack the carbonyl and add in whatever this alkyl group is. When we add that in, right, we end up getting this Cl CH3, which is the methyl group. And then at this point, after Gunyad added in, the oxygen is unhappy. It's going to push down pair of lone pairs to reform the carbonyl and then subsequently kick out the chloride. And this results in, well, a ketone. So our first equivalent makes a ketone. But we have to remember that we're in excess Grignard. So that means that the Grignard is going to attack again. So then we get this thing, right? CH3 R group. Okay. Then the oxygen is not happy. And you might think to make it happy, we can push down a pair of electrons and kick something out. But if there's none of these are really good even groups. All bad even groups. I was able to kick out the chloride because chloride becomes a negative molecule. But we should recognize that MgBr has positive charge that can neutralize the chloride. And the reason chloride can have a negative charge is because it's a highly electronegative molecule. When we have these, if we were to kick out any of these alkyl groups, carbon would have a negative charge, and carbon isn't really electronegative, so this is just not going to happen. So our second equivalent makes an abduct, which is just a salt. And as I said before, the MgBr is floating around to make that neutralize, so it's okay. Since these are all bad leaving groups, what we can do is aqueous acidic workup, which is just a source of protons. So then the oxygen can snatch a proton, and then this molecule will exist happily as a tertiary alcohol. So we've done the first two steps. So now it's time for sodium hydride. Sodium hydride is a, you draw sodium hydride. And sodium hydride exists like this, but hydrogen is a lot more electronegative than sodium. So in reality, oh, not in another reality, you could draw your molecule like this. This makes hydrogen, okay, you could be thinking like similar to our lithium aluminum hydride. Could the hydride add into the molecule? The hydride doesn't add into the molecule because there's nowhere to add in. There's already 3 individual atoms bonded to the carbon, and it's not like we can form an inert because of, and we can't form an inert and move like electrons around to be able to add in the hydride. So instead, the hydride acts as a base, and it's gonna deprotonate this. So when it deprotonates that, the electron bonds go back here, and this results in remaking the salt. See? And we kind of just like undid our acidic workup. But I think we also do it just to stabilize things. So like if it makes sense, like if you're like in your lab, you would purify your Grignard product. And we do that by doing the aqueous acidic workup first to purify it from like non-polar stuff. And then we can isolate it, and then we take the isolated product and we induce it to the sodium hydride. So then we realize that our fourth step is something that our molecule can attack. CH3 bonded to an I. Again, This is more the actual, this has a partial negative charge and this one has a partial positive charge. And we know iodine can accommodate a negative charge by itself. So it's just going to attack the carbon and the carbon's going to give the electrons to that. And so we get this molecule, R, CH3, CH3, O bonded to a CH3. And everything's happy again. And we could draw the iodine with the negative groups. It's a negative charge, and then MgBr with the positive charge neutralizing it. And this is the same as like the squiggles he drew on the answer key, but he just didn't explicitly draw the methyl groups as I did. And a really fast way to think of this is know that these two steps are going to make the tertiary alcohol. So oops. By adding in whatever is attached to the grignard as the alkyl groups. Then this step, these two steps are gonna allow the molecule to do an SN2-like reaction where you just exchange H of alcohol for whatever this is. So we get this. Oops, I forgot the oxygen. And that is our final answer. So yeah, I don't think we didn't have to know the mechanism for this one, but I think something you can is very easy to memorize is when you have this lithium, aluminum, hydride, OT-but3, it's always going to make aldehydes. I'm going to write that down. And I think we could always make aldehydes. And this is the same idea when we have this one. This one always makes methyl to copper lithium always makes ketones like lithium, like dibol always makes aldehydes. And we could for sure think of the mechanism. Like we know that this H is a hydride, so it's kind of nucleophilic. It's gonna add into that, push that up. So then we get this HRCl. Oh no, our oxygen is not happy. It has a negative charge. It's going to push electrons down. But oh no, the carbon is not happy. It's going to kick up the chloride. And so we get aldehyde. So yeah, I guess the mechanism isn't too bad. It's essentially the same thing as we've been doing before with a lot of our other molecules. So for the next slide, it's the eid, and I think I have the mechanism. The mechanism is, hold on. Okay. The great thing about this is that it showed us that the T is positively charged and the C is negatively charged. So what happens is this attacks this, which then results in H2 P H3 then O. Sorry. This I forgot to draw the electrons pushing up. But now as a result of the carbon adding in, we had to push electrons up from the pi bond to the oxygen, and then we had to, and that's all. And then we look at the molecule that we made. And what's the oxygen going to do is the oxygen's going to attack the partially positive P, because it's still partially positive. And then it's going to make yeah, it's going to make this sort of thing. Wow. Okay. So it's going to make this kind of weird thing where the P is bonded to both of them. But the P is happy now. But in a sort of interesting arrangement is okay. I'm trying to make sense of this too. Is that if these bonds are gonna break, but the way that these bonds break is sort of like the bonds between the carbon and oxygen go to this carbon and oxygen. I mean, this carbon-carbon bond. And then this bond here goes to the P. So then what we end up with is that we now have a carbon-carbon double bond. And OPPH3 in the solution. But this is our final product. And a fast way we can think of this is whatever this thing is just going to replace whatever the oxygen is. So this is my original molecule. I'm just going to erase the oxygen and then put whatever is in that part of the ethod. And I get the right answer. And this can be drawn. Oops. It can be drawn like this. And it's white. He just haven't explicitly drawn the hydrogens. So that's how you do the first page. Now we are gonna do the last page. When compound 1 is treated with chlorine, a cryocatalyst, and then aqueous sodium hydride, a Robertson annulation occurs to give compound 2 in a high yield. Compound 2 is the core of the big molecule. Ignore the cryocatalyst. Write a detailed stepwise pushing mechanism for the conversion of 1 to 2 in aqueous sodium hydride. It said sodium hydride twice, so we're probably going to use sodium hydride. And it also says Robinson annulation. With Robinson annulations, we have to remember that it is a two-part reaction, which is first a Michael reaction that makes a 1,5 dicarbonyl, which just means that 1, 2, 3, 4. There's a carbonyl at the first and fifth away from each other. Then the second part of the Robertson annulation is the intramolecular Aldol reaction plus dehydration. Um, so what happens is we're gonna first recognize that NaOH exists as Na ions and hydroxide ions. And hydroxide is a strong base. So it's going to first deprotonate a hydrogen on a molecule. Yeah, I just didn't think. It's probably gonna deprotonate this hydrogen that he has explicitly drawn here, because this is a very acidic hydrogen. So, as a result of that happening, the bonds get pushed to the carbon-carbon bond here, and then the bonds from the carbonyl get pushed up to the oxygen. And this results in this molecule. Everything else is basically untouched except for what we have drawn here. One reason why it might not attack this hydrogen here is that when it deprotonates that hydrogen, it'd be kind of weird for it to form carbon-carbon bond there. Or we just get to a point where we move the electrons around and we're kind of stuck because there's no place for electrons to move around afterwards. So we end up with this molecule, and oxygen now has a negative charge on it, which is offset by the positive charge of the sodium and H2O. This alkene is electron rich, so it has the ability to attack somewhere else in the molecule. So we know that this is a Robinson annulation, so we would want to attack somewhere that gives us a 1,5 dicarbonyl. So we can do that by counting. We have 1, 2, this center carbon here as 3, 4, 5. We could also explore other places. Maybe we could have attacked like maybe here. So 1, 1, 2, 3, 4. That's too short. And then we go the other route. 1, 2, and do another color as well. 1, 2, 3, 4, 5. Whoa, that's too short as well. Well, there is an oxygen there, but it's not a carbonyl oxygen, so these paths won't work. The only path that will work is the one that we've did in purple. So when the alkene attacks this third carbon, it pushes the electrons up here. Which then pushes these oops. These electrons push up here, which then pushes that up here and forms some sort of inlet. This molecule is like very difficult to draw. It's not, I guess it's not too bad, it's just awkward. So I don't like drawing it. But gotta do what you gotta do, I guess. So this is what we have as a result, and we can count what can happen. Oops. We still have water floating around. So we just zoom out. HOH, this alkene. Hold on, let me backtrack. We have an oxygen that's not happy because it has a negative charge on it. So it's going to push electrons down. And then this alkene is going to protonate the water we made. And we're going to get our this is we're going to get this, guys. We're going to get a dicarbonyl that has a carbonyl at the 1, 2, 3, 4, 5. So this is our micro reaction product. But we're doing a Robinson annulation. So there's going to be an intramolecular Aldol condensation. So we should also recognize that we reformed our base. So our base is going to do some work again. What our base is going to do is it's going to attack an acidic carbon. And it could very well attack one of these. But then if we attack one of those, we would just be going in reverse. So it's actually going to attack a carbon, a hydrogen on the right side of the molecule. And another reason why it would attack that side of the molecule is if we look at our beginning and ending molecule, we see that there's a bond formed here that wasn't explicitly there before. So that tells us that we need some sort of alkene on the right side of the molecule to be able to form the bond that was not previously there. So that's another reason why we would attack the white side over any other molecule. So we deprotonate that, and then the electrons go into the bond, and then we get to draw this side again. Don't forget your hydrogen for your aldehyde, or you get marked off. So now, if you remember again, alkenes are electron rich, so they can act like nucleophiles. So it's going to attack somewhere where it is electro, and not electro, wait, yes, electrophilic, that's the word. So then we know that this carbonyl on the other side is electronegative and partially negative oxygen and partially positive carbon. So it's just gonna donate electrons to there, which then pushes electrons up to the oxygen there. And this then results in uh, so, Again, this is like, this molecule is not fun to draw, at least the other part of it. And the bond we just formed here. And now we have a nitrogen with a negative charge. Let me think about the next steps. Okay, so let me erase that. I was getting ahead of myself. The next step is that, we think, now hydrogen, not hydrogen, our oxygen is not happy because it has a negative charge on it. But I didn't draw it. But in our previous step, we actually formed water. So that water is going to come back around and get deprotonated, which reforms our sodium hydrogen. So what that results in is this. I have to redraw the whole molecule again, just because I added one hydrogen to the thing. Mm, Hold on. Okay, so we have this thing, and we've regenerated our base. Now, the base is going to go. Wait, hold on. I got it. This is our aldol intramolecular aldol product smile, because we have our alcohol here and our aldehyde here. Actually, I'm going crazy. Yeah, that's technically a ketone. This is, I swear guys, this is still the aldol product. Intramolecular aldol condensation. Oh, yeah, this is still right, because this is the intramolecular aldol product, but now we're gonna do dehydration, which is just the loss of water. So what happens is our base goes a little crazy and it's not done working with this molecule. So what's it going to do is attack an acidic agent, which is these ones here. It's gonna deprotonate this, push bonds onto that, then push electrons from the pi bond up. And then, wow, I have to draw it one more time just because I took away the hydrogen. Okay, so we have a unit here. We have a pi bond here, hydrogen here, HOH. Boom, boom. Here, here. Okay, we have this alkene. And now we have to recognize that the oxygen is not happy again. So what's it going to do is it's going to take a pair of electrons and push. It's going to take a pair of electrons and make a carbonyl bond again. But then that carbon has too many things bonded to it. So the pi bond is going to move down here. But then the carbon with the hydroxide now has too many things bonded to it. But because the top one is an enolate, and the enolate initiated this electron pushing mechanism, we are allowed to kick out the hydroxide. And this results in this product. Let me say we need plus H2O. And then we make our final product. If there was, wait, let me think about how I'm going to say this. In a normal reaction, it's not really possible to kick out an hydroxyl. But because we're working with an enolate and enolates are special cases, we actually have the ability to kick out the hydroxyl. And the hydroxyl that we kicked out is just going to go with our sodium ion. So the charges are neutral out, and this is kind of a catalyst. And we still have H2O. H2O was formed. So this was basically a dehydration step, which is a part of the intramolecular aldol product formation. Occurred after the intramolecular aldol product. So the hydrogens still exist here, just in case anyone was wondering where they went. I just didn't draw them. And now we have finished the worksheet. This is just basically a bunch of proton transfer madness, the sodium hydroxide going crazy, being a strong base, wanting to deprotonate stuff. But it was pretty fun, even though we had to keep drawing that weird particle molecule. So the main thing you want to take away is that an Robertson annulation is going to have a microreaction that forms a 1,5-dicarbonyl, and it's going to be followed by an intramolecular aldol reaction, which is just where the alkene is going to attack the other carbonyl. I just realized I made a oopsies because let me check the key. I feel like that it would be hard to think that exists. Yeah. So I did make a mistake. Essentially when we form the alkene here, this should be an enolate. And it is the result of the enolate being unhappy that the oxygen being unhappy that it pushes the electrons down and then forces the alkene to attack. Other than that, everything else should be correct. Yes. Which I sort of split in misinformation with that one, but it was a small thing. So then you do your intramolecular Aldol reaction, and then when you dehydrate the molecule, you have your, I think this is a alpha beta unsaturated molecule now. Alpha beta unsaturated carbonyl. Yeah. Anderson annulation. Don't forget these two steps, and then you should be good. And then with that, I'll end the video. Okay, thanks for watching, and I hope this helps.